Hi everyone, welcome to our seventh lecture. This lecture is still in 2D kinematics. It's another special case. This is the special case of what's known as uniform circular motion. And even though I didn't write here in the title 2D kinematics, it still is part of 2D kinematics. This is another one of these joint lectures where I'll simply edit out for the non-calc students, I'll edit out all of the calculus. For the calc students, I'll use calculus to actually derive the equations that we'll use, okay, to solve problems. All right, so let me start off by saying what is uniform circular motion? Basically, it's motion which is constrained to a circle in 2D, and the motion, the object moves at constant velocity. Okay, so here I have a fairly abstract picture, and before I describe it, though, I might want to give you some real-world examples of when you have uniform circular motion. And one example, it's actually our first problem, is like driving around a corner. So if you're in a car and you're driving around a corner on a bike and you go around a corner, you feel how you have to lean into the turn, and that's because there's a centripetal acceleration, and that's an example of uniform circular motion. Another example of uniform circular motion is maybe like a sling. If you tie a stone to the end of a string and then you spin it like that overhead, and it makes a circle, and if it's the object is moving along the circle at a constant speed, well, then that's another example of uniform circular motion. Yet another example is a centrifuge, which is used in biology to separate something like blood. Okay, basically, as the centrifuge, you put these test tubes in this tray which spins very fast. Okay, hundreds of times per second, and it'll separate out the blood. The heavier stuff will go to the outside of the circle, but again, there's a centripetal acceleration because it's going in a circle. uh, um, Another example is like planetary motion. Now planetary orbits are actually ellipses, which we'll see just very briefly in the course in a little bit. But they're very close to circles. So like orbital motion is circular. And maybe one more example. I remember this as a child at Fantasy Island. And there's this ride called the Devil's Hole, and you go in there and you spin in the Devil's Hole, and it's kind of interesting because you feel like you're stuck up against the outer walls, and that's because again of the centripetal acceleration, or even a simple merry-go-round is another example of uniform circular motion. So it's in a lot of places. Okay, so it is a special case, but it's a very common special case, and so it's worth looking at. Okay, so how does uniform circular motion work? Well, first it's circular. So you can see here I have a circle in my xy plane, and the object P, which is at point P here, is constrained to be on that circle. Okay, that's part of it, but that isn't everything, because the point P could be constrained on the circle, but it could do all sorts of weird motion. It can move one way and then stop and turn around on the circle, move back, and do all sorts of crazy motion like I'm trying to indicate with my cursor here. But no, this is uniform circular motion. So it's the point P here, but it keeps turning around the circle at a constant speed. Okay, at a constant speed, and at any given instant, so this is this diagram that you're seeing here is like one particular instant in time. It's like a little picture you take. The point P is going to be at some distance r from the origin, and it's going to be at some angle theta from the positive x-axis. Okay, and so r and theta are what? There are polar coordinates for the object. Okay, and if you want to describe uniform circular motion, well, the first thing is r doesn't change, because if r changed, then you would step off the circle, so r is fixed. And the other thing, theta isn't fixed because theta keeps increasing, but theta increases constantly over time. Okay, and so you could write theta as omega times t, where omega is a constant. And guess what? Omega is our angular frequency that we saw in simple harmonic motion, but it's the same omega, but now transferred to uniform circular motion. So let's understand this formula before I move on. You could think of omega as just some number, and usually we work in radians per second, but you could even think of it in degrees per second. Suppose it's omega is 10 degrees per second. That means that your angle increases 10 degrees every second. So say at t equals 0, you're at 0 degrees, okay, like right along the x-axis. And then a second later, you're at 10 degrees. Then another second, 20 degrees. Then 30 degrees, 40 degrees, 50 degrees. Every second, you gain 10 degrees. 10 degrees more, 10 degrees more, 10 degrees more. And I think you can picture that what that means is that this object P is going to move along the circle, along the perimeter of the circle at a constant speed, okay? And so theta is equal to omega t, where omega is a constant, is how theta increases over time. So R constant, theta increasing linearly over time, that's a description of uniform circular motion mathematically, okay? And so there's the beginning of our kinematics. Okay, the next section is calculus, involves calculus, and we can now actually use our polar coordinates and derive the velocity and position, velocity and acceleration from our position graph, okay? So remember, we're in 2D, and so in 2D, there's both an x and a y component, okay? And so x and y, they both change over time, so they're not static x and static y. X is a function of time and y is a function of time. And you say, well, how do I calculate x? Well, you've got an object which is at a distance r and an angle theta, polar coordinates, and so just like I showed you when we did the lecture on vectors, x is equal to r theta, that's still perfectly legitimate. Okay, that still works. But now you have to recognize that theta increases linear over time. So I'm going to remove that theta and I'm going to replace it with omega t. So x as a function of time is just r times omega t, where r is a constant and omega is a constant. Okay. Similarly, y, if you remember from our vector lecture, is r sine theta, and that's r sine omega t. Okay, and there you go. There's x and y, that's the position, both components of the position, as a function of time, okay? Now, once you've got the position as a function of time, there's your starting point for your kinematics. How do you get the velocity as a function of time? Well, remember what we did in 1D, we differentiated, okay? But here, you've got two functions. You've got both the x, and if you differentiate that, you get vx. You get the x component of the velocity as a function of time, and you've got y as a function of time, and if you differentiate that, you'll get the velocity y as a function of time. Now, I didn't fully prove that, but I think it's fairly intuitive because we didn't do a full generalized theory of 2D kinematics. Technically speaking, I didn't prove why this happens, but it makes sense because, you've got just your x component of the position, and you say, well, at what rate is that x component changing? Well, that's going to give me the x projection of the velocity. And similarly for the y, at what rate is the y component changing? Well, the rate at which the y component is changing is going to give me the y projection of the velocity as a function of time. All right, so if we differentiate this, and we did this actually with the simple harmonic oscillator, if you differentiate r cosine omega t, you're going to get, well, the derivative of the cosine is the sine. There's an extra negative sign in front, but there's an extra factor of omega that comes out in front, and that's because of the chain rule. Because first you differentiate with respect to the entire argument omega t, and then you differentiate omega t with respect to t, and that gives you an extra omega out in front, okay? So the derivative of the x function is going to be minus omega r sine omega t, okay? And the derivative of the sine is going to be the cosine, okay? And it's positive, so I put a plus in front to emphasize that. And we still get an extra factor omega because why? Again, the chain rule, okay? And so Vx is going to be minus omega r sine omega t, and Vy is going to be plus omega r cosine omega t. Notice that the cosine was replaced by the sine and the sine was replaced by the cosine, okay? Great, now we have the velocity as a function of time, both components. That's why I put this curly bracket here, because I'm trying to show that these two numbers together, they form the vector. So if I say, what is the velocity as a function of time? Don't give me just one or the other, it's both of them, okay? And then finally, we say, all right, what's the acceleration as a function of time? Well, same idea, just take the velocity, x component, and differentiate it, and you get x component of a. y component of v and gives you the y component of a. All right. When you differentiate these again, the sine will become a cosine, but you'll get an extra omega in front. So now you've got two omegas in front. That's why there's an omega squared. And the cosine will become a sine. And again, you'll get another omega in front. So there's omega squared in front. And you'll notice this r cosine omega t. And the r cosine omega t, that's minus omega squared x. And this is minus omega squared r sine omega t. That's minus omega squared y. So the x component of the acceleration is directly proportional to x, and the y component of the acceleration is directly proportional to y. Okay. In fact, I kind of alluded to it here, and I wish I'd put this in my notes, but notice that this is r sine omega t. That's actually the y component. It's like the vx is proportional to the y, and Vy is proportional to the x, okay? And here, Ax is proportional to the x, and Ay is proportional to the y, okay? Now, why that's important will come out in my when we look at the directions in just 1 second. But before we do that, let me just define very clearly what omega is here, okay? Omega, I did sort of describe it earlier, but now it becomes a lot clearer. It's going to be 2 pi over capital T, where capital T is the period of the motion. Just like in simple harmonic motion. Okay, you can think of uniform circular motion as the 2D equivalent of uniform circular motion. Of simple harmonic motion. Okay, so uniform circular motion is the 2D equivalent of 1D simple harmonic motion. All right. Now, why is this obvious now? It wasn't when I first described it, but it is now. And that's because how many radians is it around a circle? So when you go around a full circle, you should know this from your math, that's 2 pi radians, okay? 360 degrees if we're working in degrees, but in this case, we're gonna think in radians. And so when you start at a point and you go all the way around a circle, what angle did you turn through? Well, you turn through a full 2 pi, okay, 2 pi. How long did it take you? So that's the angle that you turn through, okay? How long did it take you to turn through that angle? Well, it was one complete cycle, so that's capital T, the period. And so if you take the angle through which you turn, 2 pi, and divide it by capital T, the time it took, that gives you the angular frequency, okay? Sometimes also known as the angular velocity, okay, for obvious reasons. The words are synonymous, but I don't want to overload you with too many terms, okay? So there you go. There's the calculus derivation of velocity and acceleration from the position function. Before I give you some formulas, we're actually not going to use, again, we're not going to use these formulas directly in solving the problems. These formulas reduce down to something which is very easy to work with, okay? But before I do, let's look at the direction of x, the position, the velocity, and the acceleration. Before we look at the magnitudes, remember in polar coordinates, there's a direction and then there's a magnitude. Let's look at the direction first, okay? So that's my next slide, okay? So before I give you the formulas for the relationship between the magnitude of the position, the magnitude of the velocity, magnitude of the acceleration, this diagram here attempts to show you the directions in which these vectors are. Now here I call the position vector r with a hat on it. X with a hat on it, r with a hat on it means the same thing. So I moved the point P from quadrant 1 to quadrant 2 for no major reason, just because, you know, it's supposed to be, you know, you're supposed to consider it anywhere on the circle. So I said, you know what, let's just consider when the object gets to this point P, which happens to be in the second quadrant, okay? So at that point P, if I asked you, where is it? Okay, that's the position. Well, you know, start from the origin and then out to the position here, okay? And you can see the little hat there on my, or the head of my vector there. Here's the tail at the origin, okay? And that vector there, starting at the origin to P, that is your position, okay? That is your position at some time T, all right? Now, the next thing is, what direction is the velocity in, okay? Like, as I said, we'll look at the magnitude of the velocity in a minute, but just what is the direction of the velocity? Well, you know, this thing could actually be going counterclockwise or clockwise. I chose counterclockwise in this example, but you could turn it around, all right? In which case omega would be negative, but that's not that big a deal, all right? So, you know, just imagine, you watch my cursor here, you know, the object is going around in a circle like that. If you ask, where is this thing at any given, which way is it going at any given time? When it's here, it's going that way, okay? So I know that'll turn in a second, but you know, like, let me do this one more time. So here I'm moving, here I'm moving, here I'm moving. when I get to here, which way am I going? Well, I'm kind of going that way, right? And so the velocity vector is tangential to the outside of the circle, okay? It's actually perpendicular to the position vector. So in other words, that angle in there is 90 degrees. So the position vector points from the origin to P. The velocity vector is tangential to the circle at point P and points in the direction that you see there, okay? Now, that's actually kind of important, and it has a physical result. Like in a sling, which was like an ancient weapon of war, you would swing something like that. It's going in a circle. When you release, it actually doesn't go up. Like some people think, oh, maybe if I release it here at the top of the circle, it'll go up. No, 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 no. If you're going here and it was traveling that way, you release, it goes off that way. Okay, so the velocity is always tangential to the outside. Or I don't know, I wouldn't recommend that you do this for obvious reason. You're on a merry-go-round, you're on the outside of a merry-go-round, and you jump off the merry-go-round. Which way are you going to go? You're going to go tangential to the direction that you're traveling in, to the direction that the merry-go-round is turning. So over here, you're right there, and you jump off, you would go off in a direction like that. Okay, so you've got an idea of like the velocity, and then there's the acceleration. In what direction is the acceleration in? Turns out that the acceleration is in the exact opposite direction to the position. So the position points from the origin out to the point P. The acceleration points from the point P into the origin. And that's why this acceleration is usually called centripetal acceleration. Not centrifugal acceleration, it's called centripetal acceleration, which comes from the Latin pettere, which means to seek out. Okay, so it's a center-seeking acceleration. And anyone that's, in a car driving around a corner, and again, don't go around corners too fast. In fact, that's one of my first examples. But when you turn a corner fairly fast, you feel the acceleration. You feel that you kind of have to lean into the middle. Or when you're riding a bicycle, even more so. You're going around a corner, you actually lean your bike in towards the center. Otherwise, it wouldn't stay stable. And why is that? Well, because what you're doing as you lean in is you're actually creating an acceleration towards the center. And it's that acceleration, that centripetal acceleration, which keeps you on the circle. If for some reason I were to turn off that centripetal acceleration and you're not accelerating anymore, what does that mean when you're not accelerating? Not accelerating means that the velocity remains constant. And constant velocity means that you move at the speed doesn't change. You don't speed up and slow down. But it also means along a straight line. And so if for some reason at this point P, suddenly we turn off that centripetal acceleration, you start moving in a straight line like that, okay? And so the centripetal acceleration is the acceleration which keeps you turning, all right? Now, like I keep mentioning, I am going to give you the equation for V and A in terms of R, in terms of one another, and also in terms of the period, which is the time that it takes for one complete cycle. But before we do that, this is very interesting motion, and the reason is that the magnitude of the position doesn't change over time. Why? Well, that's the radius. So remember, magnitude is just how big is the vector. I don't care about the direction, just how big is the vector. Well, take a look at R here. R doesn't grow or shrink, because if R changed, then you'd be off a circle. Okay, it's the defining property of the circle, that every point on the circle is the same distance from the middle. Okay, so R doesn't change over time. Okay, well, actually, it turns out that the velocity, just the magnitude of the velocity, doesn't change over time either. Okay, because you're moving at a uniform speed. Okay, it could be something like 5 meters per second. You're turning, I agree, but the magnitude of your velocity, 5 meters per second, doesn't change. You're always moving at 5 meters per second, 5 meters per second, okay? Incidentally, sometimes when we say velocity, we mean the full velocity vector. Sometimes when we mean only the magnitude of the velocity, sometimes we'll call that speed, okay? And I actually use the word correctly up above, but it's not that big of a distinction. I just thought I'd mention it because this is a good point to mention it, okay? So the velocity, the magnitude doesn't change. It continues at the same speed all the way through the circle. It's only the direction that changes. And guess what? The same thing with the acceleration. The centripetal acceleration is always the same. It might be something like, I don't know, 2 meters per second squared. So it doesn't matter where you are in the circle, your acceleration is always towards the center, 2 meters per second squared. The 2 meters per second squared doesn't change. The towards the center, I mean, the direction changes because when you're over here towards the center is different than when you're over there towards the center. So depending where you are, like watch my cursor here. If you're over here towards the center is that way, right? Like that. But over here towards the center is different. So the direction of the acceleration, the direction of the velocity, and the direction of the position vector, they change, but their magnitudes don't change. And so this is very interesting because we have motion here where the only changing property of the motion are the direction of the kinematic quantities. Okay, so um, that's what I have in this try to describe here. Okay, so it's the magnitude of R, V, and A. They do not change, only their direction. Okay, and that's actually almost like a defining property of uniform circular motion. Okay, next slide. This is again for calculus only. We derived those equations, velocity and acceleration, from the position as a function of time. We can now use those equations to get the formulas for the magnitude. All right. I kind of alluded to the direction by saying, A is proportional to x and y. So ax is proportional to x and ay is proportional to y. And in fact, it was ax is equal to minus omega squared x. So you could see that that minus sign means that a and x are in opposite directions, just like you saw in that diagram. And then for the velocity, it was like vx was proportional to y and vy was proportional to x, and that's why v is perpendicular to the position vector. Okay, so there's a story with the position, but now we can use those formulas to get the magnitude. All right, now how do you get a magnitude of a vector out of the x and y components? Okay, so here's a situation where you have Cartesian coordinates and you want their polar coordinates. Well, if we want the magnitude, we're not interested in the angle, so we're not interested in that inverse tangent formula. We're only interested in the magnitude, the x and y giving you the magnitude, and that was Pythagorean theorem. Okay, and so over here I have v. Now you can think of v as just the magnitude, or what I called a minute ago, the speed. V is equal to the square root of the x component squared plus the y component squared. Okay, so when I did this for vectors, I did it for position vectors. I wasn't clear there on purpose. I was a little bit ambiguous. Am I referring to position or whatever? But it applies. It doesn't matter what kinematic quantity you're talking about. The magnitude is obtained from the x and y component by Pythagorean theorem. Okay. Now, Vx, even though I didn't explicitly write it there, it's a function of time, and Vy is a function of time as well. In fact, Vx, the function, is minus omega r sine omega t, and Vy is omega r cosine omega t. Okay, so I just took the equations that I had above for Vx and Vy and substituted them in for Vx and Vy. They have a time dependence there. Okay, and we're going to see in a second that that time dependence falls out. So we have minus omega r sine omega t, square that. And then omega r cosine omega t, square the whole thing. Okay, so that's why you see those double brackets there. Okay, so you're going to get omega squared r squared sine squared omega t, and omega plus omega squared r squared cosine squared omega t, all under the square root. Let me factor things out, okay, to simplify things. Both terms under the square root have an omega squared r squared. So there's an omega squared r squared in front of the sine squared and an omega squared r squared in front of the cosine squared. Pull that out, okay? And you could actually separate it into two square roots that are multiplied by one another. So we have the square root of omega squared r squared. And then under the remainder of the term, you have sine squared omega t plus cosine squared omega t. So if you think about this, sine squared omega t plus cosine squared omega t, it sounds like it has a time dependence, like it's going to vary over time, but it doesn't. It doesn't, and the reason is that there's a trig identity, and the trig identity is sine squared any angle plus cosine squared of the same angle always equals 1. Try this on your calculator. Like, pick any angle you like. Pick an angle like, I don't know, 37 degrees. And then on your calculator, do sine squared of 37 degrees. So you do sine of 37 degrees, square it. Plus 37 degrees, cosine, square it. And you'll see that it's equal to 1. And it doesn't just work for 37. I picked that as an arbitrary example. Pick any angle you like. And so even though the sine squared has a time dependence on it, and the cosine has a time dependence on it, when they're together like that, it's equal to 1 for all times. And so the time dependence falls out. And basically your V is just going to equal the square root of omega squared r squared. Well, it's a positive number, so you don't have to worry about pluses or minuses there. That gives you that v is equal to omega r. Okay, and that's perfectly legitimate, but the way we're going to solve it in our problems is we're just going to use v is equal to 2 pi r over t, over capital T, okay, the period, okay? And so even though there was a time dependence to the two components, when you put them together in the Pythagorean theorem, out pops something which has no time dependence at all. Don't think of capital T as a time dependence. Little t is the time dependence. Capital T is just a constant. It's just how long does it take for one cycle. And that doesn't change, as the thing keeps going around. Suppose it goes around once a second. Well, I mean, it could have gone around 20 times and it's still going around once a second, once a second, once a second. So that would be a period of 1 second, okay? And so we get that v is equal to 2 pi r over t. Okay, capital T. All right. We could have actually guessed that equation right from the beginning. All right, because what's the distance around the perimeter of a circle? So if you have a circle of radius r, the distance around the outside is 2 pi r. So 2 pi r is the perimeter. That's how much distance you travel in going around the circle once. So, I mean, it's hard to do it with a straight ruler, but in track and field, I remember when I was a kid, there was this thing you can measure, like it was like a wheel, and it would turn. And every time it would turn, it would say 1 more meter, 1 more meter, 1 more meter. You could take something like that, or you could use a string. Okay, so this is a way of measuring along a curved line, and you just walk around the outside of the circle, outside of the track, and you measure how far that is, and that would be equal to 2 pi r, where r is the radius. Okay, now if you travel the distance 2 pi r in a time capital T, you're traveling at distance divided by time, 2 pi r divided by capital T. There's your velocity, okay? So we could have even guessed that, but we actually got at it rigorously using our calculus. Now, that's the velocity in terms of r and t. What about the acceleration? You could do the same thing again. I'm not going to repeat that, because it's not, once you see it for the velocity, seeing it again for the acceleration doesn't really add much to your intuition. But you would do it again, and what you would find if you did this for the acceleration is that you would get that the acceleration, just the magnitude, not the direction, is going to equal omega squared r. And omega, remember, is 2 pi over capital T, and so omega squared is going to be 4 pi squared over capital T squared, okay? And then with the r in there, you get this formula like that, okay? And so there you go. Those are actually the formulas that we're going to use in our in solving our problems, all right? Okay, so before we jump into problems, let me give you the equations for the magnitude of the position, the velocity, and the acceleration in uniform circular motion. Well, the magnitude of the position, you don't need that. That's just r, because magnitude means how big, and the position, yeah, changes direction because, it depends where you are in the circle. But how far you are from the middle, how far you are from the origin, that doesn't change. That's just r. Great, that's done. What about the magnitude of the velocity? So the magnitude of the velocity, okay, is actually given by this formula, 2 pi r over capital T, all right? And we understood that, we can understand this formula again because 2 pi r, that is the circumference around the outside of the circle, divided by capital T, the time it takes to travel that. And so the distance divided by the time, there's your velocity. Okay, so that's one equation that we're going to use when we solve problems. Another equation, now this one is not as intuitive, okay, so you just have to take my word for it. The magnitude of the acceleration is 4 pi squared r over t squared, okay? So equations 1 and 2 give you the velocity in terms of the magnitude of r and, of course, t, and a in terms of r and t. Now, equation 1 and 2, you can actually eliminate the period t, okay, between the two, and if you eliminate the two, you get equation 3. And so equation 3 is not a new equation, but just like you saw this in, when I did 1D kinematics, constant acceleration, eliminating a time variable is very useful for some problems. So if you eliminate the period between 1 and 2 there, you get equation 3, and equation 3 says that the acceleration, the centripetal acceleration, is equal to v squared divided by r. Okay, so these are the only 3 equations that you're going to need to solve problems, and the only other thing you're going to need to know in solving problems is the relative direction of the vectors. Okay, so you need to know that the position is from the position vector is from the origin to the object. The velocity vector is tangential to the circle at the point at which the object is on the circle, and the centripetal acceleration a is towards the center. Okay, it's a center seeking acceleration. All right, we have all the theory. We can now start doing problems. All right, so my first problem is a very typical problem that's done and with for uniform circular motion. So we're driving around a corner with radius of 5 meters. Okay, that's like a corner which is like has a radius of about 15 feet. 5 meters is about 15 feet. So it gives you an idea. And I tried to make the numbers fairly real life. Okay, it might not be exact, but roughly speaking, you can imagine that a corner can be approximated as a portion of a circle. It doesn't have to be the full circle. It could just be a portion of the circle. Say a quarter of the circle. Okay, is your corner, and it has a radius of 5 meters. Okay. And our car, we're going to drive around this corner. Our car will, if you're traveling at a low enough speed, you can navigate the corner fine without skidding. But by the time you get to 5 meters per second squared, which is about half a g, that's half the acceleration due to gravity, you start to skid. Okay, let's just say that, that's how our tires work. So our car starts to skid at an acceleration of 5 meters per second squared, which means that you don't want to be turning that corner too fast, because if you're going too fast, your acceleration turns out to be bigger than 5 meters per second squared. Your back end is going to start to skid out. Okay, and so that's sort of the idea behind this problem. So again, the corner has a radius of 5 meters per second, and the acceleration, our maximum acceleration that the car can handle, is 5 meters per second squared. Okay, so question A is, how fast can we go around the corner before skidding? That makes sense. You kind of want to know that. And then part B is, suppose that the corner is only a quarter of the circle. Okay, so you don't need a full circle, just a quarter of the circle. When you're on that quarter of the circle, you're still doing uniform circular motion, even if it's not a full circle. Okay, so if the corner is just 1/4 of the circle, how long is the car in the corner? Okay, so basically, how long does it take to make the turn? All right, so that's just 1/4 of your period, right? All right, so the solution to part A, you could say, well, what did I give you? Well, I gave you the radius r, and I give you the acceleration a, and I don't give you any information about the period. All right. In fact, in part B, I'm asking for the period indirectly. I'm asking for a quarter of the period, but to get that, you need the period. And so you go, all right, well, which equation do I need? And obviously, it's equation number 3. Okay. So in equation number 3, there we go. Equation number 3, we have V. Sorry, we have A, we have R, and we want to find V. Okay, so let me just rearrange this equation, multiply both sides by r, and I get that v squared is equal to ra. Take the square root of both sides, and you always have to be careful when you take square roots, because sometimes you have a positive root and sometimes you have a negative root. But magnitudes are always positive, so don't worry about the plus or minus sign. So v is basically equal to the square root of ra. Okay, well, r is 5. And a is 5 as well in MKS units. So we have 5 meters times 5 meters per second squared. Multiplying in the square root there, you get 25 meters squared divided by second squared. I put the units in on purpose. Usually I don't put the units in if they're MKS, but I put them in on purpose because you see that if you take the square root of meters squared divided by second squared, you get meters per second. And that's exactly the units of velocity, okay? And the square root of 25 is 5, okay? And so I made my numbers very simple here on purpose. This is not meant to be very deep a problem in terms of the math, just get the intuition. And so your velocity is 5 meters per second, okay? So if you're traveling less than 5 meters per second, you can go around the corner no problem. But if you're traveling faster than 5 meters per second, you're going to start to skid. Just to give you an idea, because this is supposed to be like a real world example, let's convert this to kilometers per hour and then even to miles per hour, just so you have an idea. Okay, everyone knows that you got to slow down to go around a corner. Again, don't try this. Don't try to go around a corner at 30 miles an hour. You won't do it. You won't even your own inhibitions won't let you do it. You'll start to realize, geez, this isn't working out too well for me. So, you have to slow down when you go around a corner. This is why, okay? And so, let's take a look here. So we got the velocity is 5 meters per second. We're going to convert to kilometers per hour. And so this is the opposite of the problem that I did way back at the beginning when I showed you units. So we want to get rid of meters and go to kilometers. So 1 kilometer divided by 1,000 meters will eliminate the meters and give you kilometers. And then there's the seconds on the bottom, and you want to go to hours on the bottom in the denominator. So 3,600 seconds divided by 1 hour. Multiply that out, it turns out to be 18 kilometers per hour. Okay, the speed limit in a city is 50 kilometers per hour or 30 miles per hour. So if you convert 18 kilometers per hour, it's roughly 10 miles per hour. So basically, and it's again kind of a realistic problem. You really can't go around corners 10 miles per hour, faster than 10 miles per hour. Okay, if you try to turn a sharp corner, you won't be able to. And in fact, when you do go around corners, generally you even try to make try to make it as smooth a turn as possible. You might make your radius even bigger than 5 meters, just to make sure that everything remains stable. Let's look at that formula one more time because it's got an interesting intuition here. There's something to be gotten out of this equation. The acceleration goes as v squared over r. That means if you double your velocity as you go around a corner, your centripetal acceleration is 4 times. Why 4? Because 2 squared is 4. Okay, so if you go 3 times as fast around a corner, if you triple your velocity, tripled squared, 3 squared is 9. You're going to get 9 times the acceleration. So it's not a linear relationship, okay? Doubling v quadruples a. So a increases very fast with an increasing velocity. Conversely, r is in the denominator. So the smaller r is, the bigger a is, okay? Because if you divide by a small number, you get a big number. So you don't want to make your corner too tight because the smaller r is, the bigger your a becomes, okay? And remember, if a is too big, that's when you start to skid, okay? So this equation is a very nice equation. Gives you a very good sense about what's happening when you go around a corner. All right, part B was find the time that you're in the corner. The time that you're in the corner is actually 1/4 of the period because you're only in 1/4 of the circle. Okay, so let's get the period first, and you could use either equation 1 or 2. I picked equation 2 because it's easier, and so you have v is equal to 2 pi r over capital T. Rearranging this, t is going to be 2 pi r divided by v. Okay, and if we substitute in our numbers, I didn't even put the units in here. R is 5 meters. V is 5 meters per second. The 5 cancels out and you just get 6.28 seconds, okay? Now, that's the time if you were to go around a complete circle, but you're only going 1/4 of that, so 1/4 of that time is 1.57 seconds. So you're only in this turn for like about 1.5 seconds, okay, which again sounds fairly realistic. All right, so that was a fairly simple problem, but it illustrates uniform circular motion for you, okay, in an example that hopefully you've have some experience with. Here's another interesting one. It's a little bit more abstract, okay? How long is a near-Earth orbit? And what's a near-Earth orbit? That's an orbit which is close to the surface of the Earth. Now, you can't actually make near-Earth orbits. And the reason you can't make a near-Earth orbit is because you can't orbit right at the surface of the Earth. You can't orbit at the surface of the Earth because of air. The air friction would just simply not allow it, okay? When you're driving, you put open up the window, and you put your hand out the window, you could feel the air pushing back on you. The faster you're going, the bigger that push is going to be. Well, when you're traveling at orbital speeds, which is very fast, okay, you can't do it, okay? But we can pretend, just pretend that the Earth didn't have any air. And you're orbiting, but you're not orbiting way out 600 miles from or 600 kilometers from the surface of the Earth, which I think is called a low Earth orbit. You're not orbiting out there. You're orbiting right at the surface of the Earth, which you can do if there's no air on the Earth. Okay, low Earth orbits or low planetary orbits, they're possible, like on the Moon. Okay, so you can orbit very close to the surface of the Moon. As long as you're above any of the mountains, you're just skidding along the surface. And as you skid along the surface, you just keep going, keep going, keep going. All right. Now, I'll come back to this orbital motion when we look at orbital motion for, Newton's universal gravitational law. Okay, it turns out that orbiting is falling. Now that sounds like a shocking statement. You say, what do you mean orbiting is falling? If I drop an apple, it falls down. That's not the same as the moon going around the Earth. Yes, it is. And Newton has a very nice little argument. So we'll come back to that. So then it's not the point of this, but I just wanted to give you an idea of what a near Earth orbit is. If you could get a near Earth orbit, it would only take about 90 minutes to go around the entire Earth. To orbit the entire Earth, it would only take about an hour and a half, which is pretty neat. You could go all the way around, start at New York City, say, and then do a low Earth orbit, and then come back, go around the Earth and come back in about 90 minutes. We'll see that as, I solve the problem, because that's what I'm asking for. How long is a near Earth orbit? Okay, well, you can't do this problem unless I give you some numbers, and so I'm going to give you some numbers here, and you could just use Google to look these up. This is the radius of the Earth, okay? Because you're at a low Earth orbit, basically the radius of the orbit is the radius of the Earth. It turns out to be about 6,371 kilometers, okay? And then converting that to meters, it's 6.371 times 10 to the 6 meters, okay? So the radius of the Earth isn't that big. It's, 6,300 kilometers, all right? And what about the acceleration? Do we know that? Yeah, we know the acceleration. It's the acceleration due to gravity, 9.8 meters per second squared. Okay. Now I wrote a here because in the formulas above we have a, but that is my g. That is the acceleration due to gravity. What's keeping the object that's orbiting? What's keeping it on a circle? What force is keeping it on a circle? Gravity. Gravity is keeping it on a circle, so it's the acceleration due to gravity is your centripetal acceleration. That's what I comment here. The centripetal acceleration is due to gravity. Okay, and that's why we have a 9.8 meters per second squared like that. Okay, so we want to find the time it takes for that near Earth orbit. We have R, we have A, and we want to find capital T. And if you look at the equations above, you look through them and you see the equation number 1, that'll give it to you, because you know A, you know R, and 4 pi squared is a constant, and you want to solve for T. Okay, so just rearrange this equation here like that. And I just did it very quickly. T is going to equal, divide both sides by A, multiply both sides by T squared, and then take the square root. It turns out that the period is going to equal 2 pi square root of R over A. Okay, so this is just a rearrangement of that. All right, now substitute in the numbers. Whoops, went down a bit too far. The radius, I just gave that to you, and watch it. If you do look it up on Google, it may give it to you in kilometers, but we need it in meters, so it's 6.371 times 10 to the 6 meters divided by 9.8. I actually use 9.8 and not 10 here because I want a more accurate number, okay? And that turns out to be 5,060 seconds, which is about 1.4 hours. Okay, so it's a little less than 90 minutes, but you got the idea. On 1.4 hours, you can go all the way around the Earth. So, people have thought about, instead of taking a jet from here to Australia, could you put a little, I don't know what you would call it, but like something that could go out into space and come back and actually orbit its way to Australia. If you could do that, you would do it in actually about 2,500 seconds. It would be less than an hour, about 45 minutes. In about 45 minutes, you could go from, say, New York to Australia by just following some kind of a near Earth orbit. Okay, so that's kind of neat. There you go. So now I didn't ask this above, but here we go. We can also ask part B: how fast is a near Earth orbit? Obviously, this is going to be a pretty fast orbit because you're going all the way around the Earth once, around the whole circumference of the Earth. You're traveling the entire perimeter in just a little under an hour and a half. So how fast are you going? Well, if you take a look at those equations, we want the velocity. You could use either equation 2 or 3. I used equation 1 or 3. I used equation number 1 here. So v is equal to 2 pi r over t, and substituting that in, that turns out to be 7,900 meters per second. And it's a little hard to get your head around how fast that is. That turns out to be about 28,000 kilometers per hour. Okay, so these near Earth orbits are not at all slow. They're very, very fast, which is again why you would never be able to do this in the Earth, because the air friction wouldn't allow this. Okay, and I think you know that when meteorites hit the Earth's atmosphere, they're traveling so fast. They're traveling roughly in this range here. When they're traveling so fast that the air friction actually gets so hot that it'll actually melt the metals and break up rocks and so on. So yeah, the Earth's atmosphere is very important. It protects us from all these fast moving objects. The surface of the moon is just littered with craters because these objects come in and they hit the surface of the moon and nothing slows them down. I mean, they can come in. You can have little tiny micrometeorites, as they're called, and they'll hit the surface of the moon going at thousands of kilometers per second. Of course, they're small, but they're moving really, really fast, and so they're going to just pummels the moon with craters. Okay, the Earth, our Earth's atmosphere protects us from that. Okay, so there you go. There's an example. I'll do, of course, more problems like this during our tutorial sections. All right, thank you.